Hey everyone, it's Ken. In this video I want to show you the comparison theorem for integrals, which says that if you have two functions that are both integrable and they satisfy an inequality, say f of x is less than or equal to g of x, then, well, their integrals have to be satisfying the same inequality. That certainly makes intuitive sense. If you have the two functions, one less than the other, then the area under the smaller curve must be less than the area under the bigger curve. But let's try to give that kind of like a formal proof. So say you've got two integral functions, f of x and g of x, and let's say that for every x in their domain, f of x is less than or equal to g of x, and say that they're both defined on an interval from a to b, and they're both integrable on that interval. And then what I want to say is that the integral from a to b of f of x is less than or equal to the integral from a to b of g of x. So that's always going to be true. In other words, if you have an inequality of the two functions, and they don't have to be everywhere positive. You know, this could be negative somewhere, positive somewhere else, but this one just has to be less than or equal all the time. And then their signed areas will still satisfy that same inequality. And here's one way that you can do this. You can go straight from the definition. So let's actually see a formal proof and just calculate. So knowing that this is integrable, I can calculate it with right-hand endpoints, so I can take the limit. So n goes to infinity of this sum with n terms of f of xi times delta x. And what can I do now? Well, I need to back up for one step before going on to the very next thing in the proof. I want to explore the implications of what does it mean for f of x to be less than or equal to g of x. Certainly it means that for each endpoint x sub I, f of xi is less than or equal to g of xi. Right? Because our assumption is that one is less than or equal to the other for every single x, and in particular for these endpoints. And so therefore I can multiply both sides of the inequality by the positive number delta x and preserve the inequality. And since this is true for every single I, you know, think of this as like one inequality for every single I, for x1, for x2, all the way up to xn. I can add all these inequalities together, and I can end up with the sum of all the f of xi's times delta x being less than or equal to the sum of all the g of xi's times delta x. So from our initial statement that one function was less than or equal to the other, I now get that this Riemann sum, this right-hand approximation, has to be less than or equal to the other one. And now there's a theorem about limits. This is basically the squeeze theorem, which says that if you've got one function that's bigger than or equal to another one, then the limit of that function needs to be bigger than or equal to the limit of the other one. And that's what I've got here. So the limit of the smaller function needs to be less than or equal to the limit of the bigger function. And actually that's it. We're now finished, because this is really just the integral from a to b f of x. And I know that it's less than or equal to the integral from a to b of g of x. So if I had maybe organized that a little better, I would have started off my proof and immediately gone here and shown this inequality and said, well, because this is true, I can take the limit of both sides, and then that gives me my conclusion. So that's how you prove this, what we call comparison theorem for integrals. Let me give you a quick application of that. So suppose that you have a function that's bounded, meaning that for every single x in its domain, there has to be some number, capital M, that's bigger than all the y values. There has to be some number, little m, that's less than or equal to all the y values. That's what it means for a function to be bounded. And if it's true that a function is bounded and also integrable, then it's integral from a to b. Well, first of all, it's going to be less than or equal to the integral of constant m, which we've seen from a previous video is nothing but m times b minus a. And applying this inequality now to the constant function lowercase m and f of x, then you're going to get that now this is bigger than or equal to little m times b minus a. So geometrically what this means is if you have a function whose y values are contained inside this rectangle of height capital M and width b minus a, and also bigger than rectangle with height little m and width b minus a, then the integral, the signed area, has to be trapped between the areas of those two rectangles.